Hello again. So today we are going to move on to chapter 28, which is sources of magnetic fields. So we learned in chapter 27 that magnetic fields exert forces on moving electrical charges and currents. Well, it turns out that moving electrical charges and currents create magnetic fields as well. And so we're going to look into that today. So the basic law in question is called the Biot-Savart law. So this is the general law for figuring out the magnetic field at a particular point when you know the current. And it's a vector calculus equation. So there are a few steps, and you need to be careful and methodical about developing these steps. So we have B, the magnetic field, is equal to mu naught times I over 4 pi. Mu naught is a universal constant. We'll talk about that in a couple of minutes. And I is the current. And you're multiplying that by the integral of dl cross r hat over r squared, or you could also write that as dl cross vector r over r cubed. And so what do all those terms mean? So mu naught is like I said, it's a universal constant called the permeability of free space. It is equal to 4 pi times 10 to the negative 7 Tesla meters per ampere. And the value 4 pi times 10 to the negative 7 might seem a little bit arbitrary to you. That's because it is. It comes directly from how we define the unit of current, which we will talk to when we get to the end of this chapter. So I is the current. dl is a vector corresponding to the infinitesimal length of wire. So it has a length dl, and how that looks in xy coordinates depends on the direction of the wire or the curvature of the wire, and we'll talk a little bit about that in a couple of minutes. R, or the vector R, is points from the infinitesimal length of wire to the point where B is being evaluated. And it's R without any arrow or a hat is just the magnitude of the R vector. And then R hat is the unit vector, so its magnitude is exactly 1, and it's dimensionless. So let's do a couple of examples that illustrate how the Biot-Savart law works. So the first is to find the magnetic field at distance capital R from a long straight wire carrying a current I. So let's set up the whiteboard. So we'll make an important distinction that script R refers to the vector, whether it's the magnitude, the direction, the unit vector, whatever. And then capital R is the perpendicular distance from the long straight wire to the point where it's being evaluated. So we'll define the origin at a point along the wire that's perpendicularly below the point P where the magnetic field is being evaluated. So this distance is capital R. And so we have an infinitesimal length of wire, dl. And so the vector script R points from that infinitesimal length of wire to the point P where we're evaluating the magnetic field. So the first things we need to do are to figure out what dl is and what script R is. So we'll set up an xy coordinate system. So x is pointing in the length, along the length of the wire, and then y is pointing in the perpendicular distance from the wire to point P. So dl then is just dx I hat. It's pointing, it's just a unit of length in the x direction. And so it's pointing to the right, so it's in the positive x direction. Now, what is R? R has, well, its y component is probably easiest to figure out. It's always going to be capital R. So you have plus capital R j hat. So no matter where you are along the wire, the y component of script r is just going to be capital R. But what's the x component? Well, at the origin, there's not going to be an x component. It's just going to point straight up. If you're to the left of the origin, that means the x coordinate is negative, but the x component of the r vector is positive. And if you're to the right of the origin, then the x coordinate is positive, but the x component of the r vector is negative. It points to the left. So you have x I hat, and it's going to be negative x I hat. So when x is negative, the script r vector points to the right, and when x is positive, the script r vector points to the left. So figuring out dl and r are the hardest part. Now let's do some of this qualitatively first. So you point your fingers in the direction of the wire, you curl them in the direction of the towards point P, and your thumb is pointing out. So the magnetic field at point P is pointing out of the border in the positive z direction. And if we were to move point P in a circle, what you would see is that your thumb would rotate as well. So that B actually moves in a circle around the wire. And so, that's an important qualitative analysis. So B moves in a circle and that if you were to draw a circle centered on the wire with a radius capital R, the magnitude of the magnetic field does not change. So B without the arrow, so the magnitude, B is constant around, B is constant if R is constant. And again, that's the magnitude of B. And that's going to come into play when we talk about Ampere's law in a little bit. So the magnetic field is constant along that circle, but how do we figure out the magnetic field? At least by integration. So we have dl, we have r. We need to figure out dl cross r. So you can set up the determinant and excuse me, I'll draw this line a bit straighter. So you can write the cross product as the determinant of a three-dimensional vector. So the x, y, z components of dl are dx, 0, 0. And then the components for r are negative x, r, 0. So let's evaluate that. So in the I direction, that's 0 times 0, which is 0, minus 0 times r, which is also 0. So there are no components in the I direction. In the j direction, 0, negative x minus dx 0. So there are no components in the j direction. There are only components in the k direction, and that's dx times capital R, and then minus 0. So that becomes r dx k hat. So that's the cross product vector. And so now we can set up the law of Biot-Savart. So B is equal to mu naught over 4 pi, mu naught I over 4 pi, times the integral of dl cross r divided by, and that's script r, divided by script r cubed. Now, script r is just the magnitude of the r vector, and so it's the Pythagorean rule. You square the individual components and you add them together. So script r is equal to the square root of x squared plus capital R squared. So now we have enough information so we can set up the integral b is equal to mu naught times I over 4 pi times the integral. So dl cross r, that's r dx k hat. And then r is the square root of x squared plus r squared. R cubed is x squared plus capital R squared to the 3/2. And it's an infinite length of wire. So you're going from negative infinity to positive infinity. So that's the integral we're going to be evaluating. So we've done the hard part, or the integration part is actually easy. The vector analysis is the hard part, but we now have an integral we can work with. So how are we going to work with that? Well, and we did something similar with the long straight wire when we were evaluating the electric field. So we have this we have this term. It's not that easy to evaluate directly. So what can we do? Well, we can apply a substitution. So we have x as the horizontal component of r, and so we'll say that the angle, so that the r vector is making an angle theta with the line perpendicular from the origin to the point P, and that theta goes from negative infinity to positive infinity. So we'll let x equal capital R times the tangent of theta. So to differentiate that, because we're going to need dx, that's equal to r. The derivative of the tangent of theta is the secant squared theta. And then x squared plus r squared. This is a bit more complicated. So x squared plus r squared is equal to, and that's capital R, so capital R squared tangent squared theta plus capital R squared, which we can factor out into capital R squared tangent theta, or tangent squared theta plus 1. So maybe you know the trig identity for this, but in case you don't, we'll write it out. So that's capital R squared. We'll put cosine squared theta in the denominator. Now, tangent squared is sine squared theta over cosine squared theta. And then 1 is simply the cosine squared theta over cosine squared theta. But notice how this looks. Sine squared theta plus cosine squared theta equals 1. So this becomes 1 over the cosine squared theta, and the inverse of the cosine is the secant. So you can write this as r squared secant squared theta. So now we can write b as equal to mu naught I over 4 pi. In the numerator, you have r times dx. So that becomes r squared secant squared d theta. And again, you're going from negative pi over 2 to positive pi over 2. Because at negative pi over 2, this x is negative infinity, and at positive pi over 2, x is positive infinity. In the denominator, x squared plus r squared is r squared secant squared theta, but you're taking that to the 3/2 power, so that the 2's become 3's then. So this is r, capital R cubed, secant cubed theta. So you can see that this problem then simplifies pretty quickly. So r squared over r cubed, or capital R squared over capital R cubed, is 1 over capital R. So we can write on the outside mu naught I over 4 pi capital R, and don't forget the k hat term for the vector. And that's negative pi over 2 to pi over 2. That's secant squared over secant cubed. My apologies again. So that becomes 1 over the secant, but that's just the cosine. And again, you have the k hat. So that becomes mu naught I over 4 pi r. And you're evaluating the sine of theta, because that's what the integral becomes. And you're evaluating that from negative pi over 2 to pi over 2 with the k hat. So that's mu naught I over 4 pi capital R. The sine of pi over 2 is simply 1, and you're subtracting from that the sine of pi, the negative pi over 2, which is negative 1. So 1 minus negative 1 is just 2. So in the end, what you get is mu naught I over 2 pi r. And it's in the k hat direction. So, and we know, again, just from analyzing it qualitatively, that B is going to make a circle, that if you were to move point P in a circle of radius capital R around the wire, that B would rotate with it and always be perpendicular to both the wire and to the perpendicular line from the wire to point P. And so B makes circles around the wire. And for a given value of capital R, B is going to have a constant magnitude that's equal to mu naught I over 2 pi capital R. And so you can introduce a third right-hand rule out of this, that you point your thumb in the direction of the current, your fingers will curl in the direction of the magnetic field. So the magnetic field, like I said, is making circles around the wire, and you can figure out the direction of the magnetic field from the right-hand rule. That brings us to our next example of the Biot-Savart law. So we're going to find the magnetic field for a point on the axis of a circular loop of radius capital R. So again, we're going to distinguish between capital R and script R, which is the vector. But the point is a distance z away from the center of the loop, where z is a point along the axis. So we're going to define the z-axis as the axis of the loop, and then the loop is going to, itself is going to be in the xy plane. So let's get back to the whiteboard. So we'll do a head-on view first. I'm not one for three-dimensional drawings. So we have a head-on view. You have capital R, that's the radius of the circle. And then the side view, that's not what I wanted to do. You have the plane of the loop. And we'll draw a perpendicular line through the center. And so point P is along that axis. And so again, we have the radius capital R. And so we'll draw DL up there. And so that vector goes from a point on the circle to point P. So again, the first things we need to do are to figure out DL and R. Before we do that, though, let's look at this qualitatively. So from the right-hand rule, you point your fingers in the direction of the current, you curl them in the direction of, you curl them towards point P, which is towards the center of the circle, and then out up in the Z direction. You'll see that the magnetic field is pointing in towards the center and also up a little bit towards the point P. What you'll notice is that if you spin it in a circle, the X, Y, Z components will cancel each other out while only the Z component remains. So you expect the magnetic field to point up the axis of the circle. So now we'll see how that looks mathematically. So we'll start with DL. DL is pointing along a circle in the XY plane. So we're going to say at a given point that we're looking at DL, it's making an angle of theta with the reference line, where the reference line is going to be defined as theta equals 0. So at theta equals 0, DL is pointing directly upwards. So there's no X component, but the Y component is the maximum value it's going to be. So at theta equals 0, the cosine theta equals 1. So we would expect the Y component to be related to the cosine of theta. Remember, the cosine of theta is equal to 1, and it's positive. So we'll say plus cosine theta J. Now let's look at the top. So we're defining it as a counterclockwise current. So at the top, the current points to the left. And so that direction is, that choice is arbitrary. But if it's clockwise, everything is reversed. So at the top, it's pointing to the left. So it's in the negative X direction when the sine theta equals 1, but there's no Y component. So again, the cosine of theta, if theta is 90 degrees, is 0. So there's no Y component. So this is still holding. But it's pointing to the left where the sine of theta is equal to 1. So why don't we write negative sine theta I? And so that is DL. And so if we're at 180 degrees, it's pointing straight down. So the sine of 180 degrees is 0. The cosine of 180 degrees is negative 1. So you're pointing straight down. But you're still multiplying these terms by the magnitude of the vector. Now, DL is basically an arc, a length of arc on the circle. So the magnitude is going to be capital R, the radius of the circle, multiplied by d theta. And so that's important to keep in mind when you're doing this. And so now you have a value for DL. And again, so these are the components or the XY components of a vector that's pointing in a clockwise or counterclockwise circle. And if you reverse the components, that's a clockwise circular motion. But to find the magnitude of the vector, that's just capital R d theta. And then these define the direction. Now we want the vector R. And that's script R. Now there are two things to notice. One, you're pointing from the circle to its center and then out in the Z direction. So the z component is easy. It's the value z. So you're going to have plus z k hat. Now, as far as the x and y components are concerned, you're pointing into the circle. If you were drawing the r vector from the origin or from the center to the point on the circle, it would be capital R cosine theta plus I hat plus capital R sine theta j hat. But we're pointing in the opposite direction. We're going from the circle in towards the origin, so we need to take the negatives of those. So that's negative capital R cosine theta I hat minus R, and what I will do, minus R sine theta j hat, and that's capital R, plus z in the k hat direction. So, and again, this is assuming a clockwise, that from the vantage point of point P, you're rotating clockwise. Or excuse me, I keep saying this wrong. From the vantage point of point P, if you're looking at the current loop, the current is rotating counterclockwise. And that's how you get this value of R. And if it were rotating clockwise, you would reverse dl. And that would give you the opposite directions when you do the cross product. But let's set this up. So dl cross R. Again, we'll set this up, and that's script R. And we'll set this up in determinate formation, notation. So I hat, j hat, k hat. dl is negative R sine theta, or capital R sine theta d theta. And then R cosine theta d theta. And 0. Let's draw this out a little bit better. So that's j hat and k hat. So those are the components of dl. And then the components of R are negative R cosine theta, negative R, capital R, sine theta, and z. So let's look at this. In the I hat direction, you have capital R cosine theta d theta z minus 0. So we've got rz cosine theta d theta I hat. In the y direction, so that's 0 minus, and you have a negative r, so that's positive r sine theta d theta times z. So this becomes plus r, capital R z sine theta d theta j hat. And then in the k direction, the negatives cancel out, so it's r squared sine squared theta d theta. And then you minus here, but the negatives cancel out again, and so it's plus r squared cosine squared theta d theta. That becomes plus r squared d theta. Remember, the sine squared plus cosine squared equals 1. So that's r squared d theta k hat. So again, going back qualitatively, I said when you evaluate it over the full circle, the x and y components should cancel out. So we're going to see if that's true mathematically. And leaving you only with the z direction. So let's clear some space up. And d theta is going to be from 0 to 2 pi. It's going to be over the full circle. So and the other thing, so we have B is equal to mu naught I over 4 pi times the integral, and that's from 0 to 2 pi. So we're going to put r cubed on the bottom, or script r cubed. And that's just the magnitude of the script r vector. So you basically square the individual components and add them together to get the magnitude, and then cube it. And so it's the square root of capital R squared plus plus c squared, but you're cubing that. So that becomes capital R squared plus c squared to the 3/2 power. Notice we're not integrating over z, so this is a constant term. So we have in the numerator then rz cosine theta d theta I hat plus rz, capital RZ, sine theta d theta j hat plus capital R squared d theta k hat. So that's what you're integrating over 2 pi. Now here's where things simplify quite a bit. So you have the cosine theta d theta. And it's over a complete circle. And now the cosine is going to be positive half the time, it's going to be negative half the time. So over a complete circle, the integral is going to be 0 if it's just the cosine by itself. And the same thing applies for the sine theta. When you integrate over d theta, it's just going to be 0. So again, we have these terms cancel them out. So I'll break it up in 3 so you can see what's going on. So you have mu naught I over 4 pi. And so we'll include the r squared plus c squared to the 3/2 power. And so we'll break it up into 3 integrals. So we have rz times the integral of cosine theta d theta I hat from 0 to 2 pi plus rz times the integral from 0 to 2 pi of the sine of theta d theta j hat plus capital R squared times the integral from 0 to 2 pi d theta k hat. So let's look at this integral first. The cosine theta, the integral of that is the sine theta evaluated from 0 to 2 pi. Well, the sine is going to be the same at 2 pi as it is at 0. So that becomes 0, just doing the math. And then similarly, this integral is the negative of the cosine theta, but you're looking at the cosine of theta at both 0 and 2 pi. The cosine is going to be 1 in both places, so 1 minus 1 equals 0. So this is also 0. And here, you're just evaluating d theta from 0 to 2 pi. That's very simple. It's just 2 pi. So you plug those values in. So you get mu naught I over 2. So you have 2 pi over 4 pi. So that becomes 2 times the square root of capital R squared plus c squared to the 3/2 power. And that's in the k hat direction. So you have the magnitude and you have the direction. And so that brings us to another right-hand rule. This is right-hand rule 4. So if you have a circular current, you curl your fingers in the direction of the current, the finger points in the direction of the magnetic field. So if we drew a clockwise loop, the current would point in the opposite direction. It would point into the board, or the negative K direction as we defined it. But notice how this right-hand rule is very similar to right-hand rule number 2, which is for the magnetic dipole moment. That's telling you that the magnetic dipole moment, or the direction of the magnetic dipole moment vector, corresponds with the direction of the magnetic field generated by that current. So again, talking about rotating electrons in iron, the potential energy is minimized when the dipole moments line up with the magnetic field. So what's basically happening is, if you expose iron to a magnetic field, you make the iron magnetic, because the iron has lots of dipole moments from electrons circling around, but they circle around in random directions if there's no magnetic field forcing the issue. They rotate in random directions, so the net magnetic field is 0. But if you expose it to a magnetic field, then all those dipole moments line up, and their corresponding magnetic field vectors line up accordingly. And you have these magnetic fields start to add up, and so you effectively magnetize the iron. And again, that's how you're able to attach a bar magnet to a refrigerator, for example. But that's also how electromagnets work. You wrap a current around a piece of iron, and when you turn the current on, the loops of wire create a magnetic field. That's going to magnetize the iron so that the dipole moments within the iron line up, so that magnifies the magnetic field significantly. So a coil of wire by itself doesn't produce that strong a magnetic field, but a coil of wire with a piece of iron inside it can become a very powerful magnet. And so that's basically what an electromagnet is. And it also makes it possible to greatly magnify the self-inductance of a circuit, which is something we're going to talk about in Chapter 30. So that brings us to Ampere's law. So you've seen it the long way. Now we're going to show you the short way. And for a long straight wire, it's very, very easy. We were already able to figure out qualitatively that the magnitude of the magnetic field, if you were to draw a circle centered along the wire, that the magnitude of the magnetic field would be constant along that circle. So that comes into play in Ampere's law. So Ampere's law is similar to Gauss's law, that it's a magnetic relation that you can derive from the Biot-Savart law, the way you can derive the Gauss's law from Coulomb's law. But Ampere's law can be applied in any place where there is symmetry to make a complicated integral equation a simple algebra equation. So around any closed path, again, the shape of the path, the size of the path don't matter. But if you were to take the dot product of the magnetic field vector and the line in question and integrate over that fully closed path, the result would be mu naught time multiplied by the current that crosses through that loop. So it crosses through that closed path. So how does that work with a long straight wire? Well, your Amperian loop, the equivalent of a Gaussian surface, is a circle of radius r around the wire. And again, we've already figured out qualitatively before we did any of the integration that the magnitude of B was going to be constant along that loop, and that it was going to make a circle around that loop. So B dot dl over the full path is just B multiplied by the circumference of the circle, which is 2 pi r. So if you have a wire of current I going through that loop, then the magnitude is, or B times 2 pi r, is equal to mu naught I. And then solving for B, you get mu naught I over 2 pi r. So you see it's much, much simpler than doing the integral. But the law can be derived from Ampere's law. But again, it makes some applications much simpler. So the magnitude of a long straight wire is mu naught times I over 2 pi r. And the direction is that it makes circles around the wire, and you can use the right-hand rule. Point your thumb in the direction of the current, your fingers curl in the direction of the magnetic field. So let's do an example. If an electric wire is allowed to produce a magnetic field no larger than that of the Earth at a distance of 15 centimeters from the wire, what is the maximum current that the wire can carry? So we're given a value of B, and we're given the distance, and we know what mu naught is. So what is I? So let's go to the whiteboard. So B is equal to mu naught I over 2 pi r. And one thing you'll notice with these long straight wire problems, mu naught is 4 pi times 10 to the negative 7. Often the easiest way to do this with the calculator is just do this division first. So you have 2 times 10 to the negative 7 multiplied by I and divided by r. But here we're actually asked to solve for I. So you're multiplying both sides by 2 pi r and dividing by b's, or dividing by mu naught. So I is equal to B times 2 pi r divided by mu naught. So we're told that B is simply 0.50 times 10 to the negative 4 Tesla. And then that's times 2 pi. And the radius, or the distance you are away from the wire, is 15 centimeters, or 0.15 meters. And you're dividing by 4 pi times 10 to the negative 7 Tesla meters per ampere. So again, here in this case, you're going to want to divide by 2 times 10 to the negative 7. And that'll make doing the calculation simple. So you have 0.5 times 10 to the negative 4 times 0.15 meters divided by 2 times 10 to the negative 7. And that gives us 38 amperes to two significant figures. And so that's the answer to the problem. That's as strong a current as you need. So now we're going to do another example. A 2.55 millimeter diameter copper wire carries a 33 amp current uniform across its cross-section. So we're asked to determine the magnetic field at the surface of the wire, inside the wire, 0.50 millimeters below the surface, and outside the wire, 2.5 millimeters from the surface. So again, we're going to draw a circular cross section. So we're not treating the wire as simply a line. We're treating the wire as a three-dimensional cylinder. And we're asked to figure out the magnetic field at a few different points. So it's a 2.5 millimeter diameter copper wire. So we know the radius is equal to 1.25 millimeters. So we're asked to figure out the magnetic field at the surface of the wire. Now using Ampere's law, you draw an Amperian loop at the surface of the wire. The entire current is enclosed by it, so that B is equal to mu naught times I over 2 pi r. And so we'll make capital R the the radius, and then r is just the distance from the center to the point you're looking at. So you're at the surface of the wire. So that's, and this is part A, mu naught I, we're given that I is 33 amps. Divided by 2 pi. And we are told that we're at the surface of the wire, so that's at a distance 1.25 millimeters away from the center. So that's 1.25 times 10 to the negative 3 meters. So again, mu naught is 4 pi times 10 to the negative 7. So we can just write this as 2 times 10 to the negative 7 times 33 divided by 1.25 E3 negative. And that gives 5.28 times 10 to the negative 3 Tesla. So that's the magnetic field at the surface of the wire. All the current is inside. So much like with Gauss's law and with the sphere, the magnetic field, as long as you're outside the wire, is going to be the same as if the wire were simply a line rather than a three-dimensional cylinder. So now we're inside the wire at 0.5 millimeters below the surface. So this is part B. So we'll do that up here. So part B, so it's inside the wire and it's 0.5 millimeters below the surface. Okay, so that's 0.50 millimeters. And so that's below the surface. So we want an Amperian loop. So we're going to draw a circle around the center of the wire with the radius of 1.25 millimeters minus this 0.50. So small r, the radius of the Amperian loop, is equal to 0.75 millimeters. So you have B times 2 pi r is equal to, and so B is going to be constant along this loop. It's equal to mu naught times the current enclosed. So the current enclosed is I, the total current, multiplied by the area within the loop. So that's pi small r squared divided by the total area, which is pi capital R squared. So to solve this for B, you divide both sides by 2 pi small r. So that's mu naught I. And you're dividing by r. So notice it's linear. So the magnetic field starts at 0 and increases linearly as you move out until you get to the surface. So that's the exact same thing as a uniformly charged sphere. Or that's very, very similar to the uniformly charged sphere. So it's mu naught times I times small r divided by 2 pi times capital R squared. So that becomes 4 pi times 10 to the negative 7 Tesla meters per ampere times 33 amps times small r, which is 0.75 times 10 to the negative 3 meters, and divided by 2 pi. And capital R is 1.25 times 10 to the negative 3 millimeters, or rather meters squared. So you need to express these in meters in order to get your answer in Tesla. So again, that's just 2 times 10 to the negative 7 times 33 times 0.75 times 10 to the negative 3 divided by 1.25 times 10 to the negative 3, and you're squaring that. And so you get 3.1, and we should be doing these into two significant figures. So that's 3.2 times 10 to the negative 3 Tesla. So it's 5.3 times 10 to the negative 3 Tesla at the surface. You're increasing linearly as you go out. So it's 0 at the center. Here it's 3.2 times 10 to the negative 3 when you're about 3/5 of the way there, I guess. So, okay then. So that brings us to part C. For part C, you're outside the wire 2.55 meters from the surface. So small r here is the 2.5 plus this. So that's 3.75 millimeters. And you're outside. So again, you can treat this as just being a wire as opposed to being three-dimensional. So then that B becomes, or a line as opposed to being three-dimensional, mu naught times the total current divided by 2 pi r. So that's 4 pi times 10 to the negative 7 Tesla meters per ampere times the current, which is 33 amps, divided by 2 pi divided by 3.75 millimeters, or rather times 10 to the negative 3 meters. So that's 2 times 10 to the negative 7 times 33 divided by 3.75 times 10 to the negative 3. And that gives 1.8 times 10 to the negative 3 Tesla. So it starts at 0. It increases linearly until you get to the surface, and then it decreases inversely with distance once you get past the surface. And again, it's just like it were a line as opposed to a cylinder, and if you're outside the surface. Okay, so that's that example. And so now we're going to move on with the discussion. Now we're going to look at two parallel conductors carrying a current. So again, currents create magnetic forces, fields. Magnetic fields exert forces on currents. So if you have two currents near each other, they should exert a force on each other. And we can evaluate this. So we're going to have two, I'll derive this for two parallel currents going in the same direction. And so we're going to find the force per unit length, L. So clear this. So we'll do a side view first. So we have two wires. We'll have the currents going up in the same direction. And they're separated by a distance d. So, and we'll call this I1 and I2. So, we'll do the overhead view now. So we have I1 and we have I2. I1 and I2 both point out. So let's figure out the magnetic field due to B1, or due to I1. So we'll call that B1. From the right-hand rule, the thumb points in the direction of the current. Your fingers curl in the direction of the magnetic field. So it's going to be counterclockwise from our vantage point. So B1 is equal to mu naught I1 over 2 pi r. And it's going to be counterclockwise. We'll define so this is B1. We'll let B12 equal B1 at the location of I2. So the magnetic field due to current 1 at the location of I2, so it's going to be up from our vantage point. So so the magnetic field due to current 1 at I2 is equal to mu naught I1 over 2 pi r, 2 pi d. Remember, they're separated by a distance d. And we'll call that j hat. And the reason we'll call that j hat, we'll set up x, y directions like this. So they're separated in the x direction. And so the current is pointing up, which is in the y direction. So that's B12. So now we have the current due to, or the magnetic field B2 due to I2. So the current is, or the magnetic field is going to make a circle. Again, it's going to be counterclockwise. So B2, its magnitude is going to equal mu naught I2 over 2 pi r. But B21, the magnetic field due to I2 at the location of I1, the magnitude is going to equal mu naught I2 over 2 pi d. But notice from the way it's circling, at the location of I1, the magnetic field is going to point down. So that's in the negative j hat direction. So the magnetic fields point in opposite directions, but we're not interested ultimately in the magnetic field. We're interested in the force. So the force and so the currents are pointing out, which is the z direction. So why don't I add that component there. So the currents are pointing out, which is the positive z direction. So the force of current 1 acting on current 2 is equal to I1 L1 cross B12, right? Well, no, it's I2 times L2 cross B12. So the L1 and L2 vectors are going to be the same because it's just the length of the wires in each case. And I should have an equal sign in there. So L points out of the board, B points, so in the first case, it's pointing up. So it's out of the board and pointing up. So the force acting on current 2 is to the left. So F12 is to the left. So again, using the right-hand rule, you point your fingers in the current, you curl in the direction of the magnetic field, which is right, you point your fingers in the direction of the current, which is out of the board. You curl in the direction of the magnetic field, which when you're talking about wire 1 acting on wire 2 is upward. Your thumb points to the left. So it's towards I1. And so what you get is I2 times L times B12, so or the magnitude of it, that's mu naught I1 over 2 pi d. And so you can write that as mu naught, as the force per unit length is equal to mu naught I1 I2 over 2 pi d. So that's the magnitude of the force. And so again, F12 is the force of current 1 acting on current 2. So now you work in the opposite direction, or you do the force of current 2 acting on current 1, but notice now the magnetic field is down. So the current points out and now points down. So the force acting on current 1 is to the right. So the magnetic field due to current 2 points, current 1 points out. The force, or the field due to current 2 points down. So the force of current 2 acting on current 1 points right. So F21 points to the right. So if you notice, they attract. And if you go through the steps for F21 over L, you get the same magnitude force. And you expect that simply from Newton's third law, that every action has an equal and opposite reaction. So you expect them to exert equal and opposite forces on each other, and they do. When the currents are pointing in the same direction, they will attract each other. When the currents are pointing in opposite directions, they will repel each other. So with that, let's pull up an example. So again, the currents attract when they point in the same direction, they repel when they point in the opposite direction. So let's do an example. Determine the magnitude and direction of the force between 2 parallel wires 25 meters long and 4.0 centimeters apart, each carrying 35 amps in the same direction. We can figure out the direction right away. They attract each other. They're pointing in this, the currents are pointing in the same direction, the magnetic force will be attractive. And now for the magnitude of the force. So it's 25 meters long, so we're approximating them as long straight wires at this point. We're assuming that the effects of the, the effects of the magnetic fields at the edges of the wire don't negligibly affect the end result. So we can still use this long straight wire approximation. So we have the magnitude of the force, and this is per the magnitude of the force. And so we'll put the L, we'll multiply both sides by L. So it's mu naught I1 I2 L over 2 pi d. So again, the magnitude of the magnetic force is just I, the current being acted on, times L times B, which is the magnetic field due to the current in question. So you have, we'll say we're looking at the magnetic field due to I1. That's mu naught I1 over 2 pi d. So that's the magnetic field times I2 times L. And it works the opposite way as well. But the important thing to remember is if they're going in the same direction, they will attract. If they're going in opposite directions, and you can do that derivation yourself, they repel. So it's 4 pi times 10 to the negative 7 Tesla meters per ampere times I1 and I2. So we know that I1 and I2 are both 35 amps. So that's 35 amperes squared. The length of the wire is 25 meters. And you're dividing by 2 pi. So again, we'll just use 2 times 10 to the negative 7 in the calculator. And D is 4.0 centimeters. That's 0.040 meters. You want to keep everything in SI units so that your answer is in SI units, which in this case are newtons. So that's 2 times 10 to the negative 7 times 35 squared times 25 divided by 0.04. You get a force of 0.15 newtons. Not necessarily large, but you would probably notice it. And that brings us to something I've been hinting at all semester. And that's the definition of the ampere. So the official definition of the ampere, in which from which all the other units and epsilon naught, mu naught, all the the electrical and magnetic constants are ultimately derived, comes from this. If 2 long parallel wires 1 meter apart carry the same current, and the magnetic force per unit length on each wire is 2 times 10 to the negative 7 newtons per meter, the current is defined to be 1 ampere. And so that's how you define the unit of current. From that you get, again, the coulomb, the volt, the farad, the ohm. You also get the Coulomb constant. You also get epsilon naught. You get mu naught. You get the Tesla. All those values come from that definition of the current. One thing to keep in mind, though, that there are some electrical and magnetic quantities, like the time constant for the RC circuit that we talked about, for example, that do not ultimately depend on the definition of the ampere. And we'll see that the product of mu naught and E naught does not, or an epsilon naught, excuse me, does not ultimately depend on the ampere either. And it depends on a universal constant that you've already looked at least a little bit. But we'll get to that in Physics 3. And that brings us to the last thing I want to talk about, and that is a solenoid. A solenoid is important because it makes it possible to create uniform magnetic fields. So a solenoid is, and let's see if I can get one out so you can see it. It's a tightly wound coil of wire. So it's a tightly wound coil of wire. You see you have this copper, it's wrapped around in circular loops. So you basically have a cylinder. In this case, the cylinder has air inside. There's nothing special within it. And so you put a current through the coils of wire, you'll get a magnetic field. And as it turns out, from Ampere's law, and I'll refer you to the textbook for the derivation, you get a uniform magnetic field inside the solenoid. And that magnetic field is equal to mu naught times the total number of turns, capital N, divided by the length of the cylinder, times I. You can also write that as mu naught times small n times I, where small n is the number of turns per unit length. And so the right-hand rule, we'll call this right-hand rule number 4. It's the same for the magnetic field due to the loop of the wire. You curl your fingers in the direction of the current, your thumb points in the direction of the magnetic field. A variation of the solenoid is called the toroid. Instead of having a cylinder, you have a donut shape. And so to show you how this looks. So this is a toroid. The really large particle accelerators employ toroids. But so basically, instead of a cylinder, you have donut shape. You have a hole in the middle, and you're looking at the magnetic field a distance r from the center of the curvature, but you're curling the wire around the solenoid like this. And obviously, you know, in real life, it's going to be more tightly wound than I'm making this look, but this is basically the idea. And a toroid is not exactly uniform, but if r, the distance from a point inside the solenoid to the center of curvature is large compared to the width of the toroid, so the dimensions of the toroid itself are tiny, but the radius of curvature is large, then it's approximately constant. Then it's constant to a good approximation. But the exact value of the magnetic field inside a toroid is equal to mu naught times capital N, the total number of turns, times I, the current going through those turns, divided by 2 pi r, where r is the radius of the point within the toroid to the center of curvature. Which brings us to one last example for today. A 40.0 centimeter long solenoid, 1.35 centimeters in diameter, is to produce a field of 0.385 millitesla, so that's 10 to the negative 3 at its center. How much current should the solenoid have if it has 765 turns of wire? So let's set up the equation for the solenoid. B is equal to mu naught capital N divided by L times I. And so we are asked to find I given all the other dimensions. So let's solve this for I. So you multiply both sides by B. So that's B times L divided by mu naught times N. Notice you can't, there's no pi term here to cancel things out for you. So what I recommend doing there is dividing by pi and then dividing by 4 times 10 to the negative 7. But let's write these numbers in. So the magnetic field is designed to be 0.385 millitesla. And then the length is 40.0 centimeters. So 0.400 meters. Mu naught is 4 pi times 10 to the negative 7 Tesla meters per ampere. And we have a total number of 765 turns. So you plug that in. And then, like I said, I recommend dividing by pi and then dividing by 4 times 10 to the negative 7. And when all is said and done, you get a current of 0.160 amperes. And again, the key to this solenoid is, and what makes it useful, it's kind of like the infinite sheet with electric fields. The infinite sheet gives you a uniform electric field. The solenoid gives you a uniform magnetic field. And that's very useful for laboratory experiments. It's also useful in high energy physics. You use the uniform magnetic field to create collisions. And so with the toroid, you know, if you have the really large like the RIC, or the particle accelerators like the RIC, or the one at CERN or at Fermilab, they have very large values of R, but the width of the toroid itself is narrow in comparison. So the magnetic field is essentially uniform inside. And so there are some important practical applications to that. Okay, so as usual, if you have any questions about Chapter 28, do not hesitate to email me and ask for help. And so I will see you next time, and we will discuss Chapter 29, which is probably the most important physical concept we'll cover this course, and that's Faraday's law of induction.